Thank you, everybody, for coming. My name is Dmitry, and I'll be speaking about semantic caching. Ooh, that was a weird echo. Okay. I work at Oracle. I lead a team where we offer OCI cache managed Redis. Okay. I'll stand here. All right, so I work at Oracle, where I lead a team, and we offer a managed Valkey and Redis service. Some of our engineers are actually here. But personally, I've used Redis and Valkey for many years. And as part of participation in the Valkey project, I maintain an SDK to build modules in Rust. How many people have built modules? How many people have done it in Rust? All right, so if you're interested in trying it out, come talk to us, to myself, and I can introduce you to other people. But we really like it because it enables us to extend Redis and Valkey functionality, but do it without forking the code, which is pretty important if you're running a cloud operation. So a little bit of a history of modules in general. So Redis got started many years ago, and about 10 years ago, they introduced the concept of modules, and the very first module they built was called Ready Search. And they were targeting full-text search and hoping to compete with Elasticsearch. So you will see it in their commands. They begin with ft search, ft create, and ft stands for full text. When Valkey emerged a couple years ago, we created a Valkey search module, which is not built in Rust. But Valkey search started targeting semantic search, vector similarity search as the first use case, versus Ready Search started with full text and later added vector similarity search. But a recent release of Valkey search module introduced, it's largely compatible with Ready Search. So if you're trying both with the latest versions, you should be really close. Okay, let's briefly review the general concept of caching. Why do we use caching? We want to decrease the load on our databases, and sometimes we want to decrease unnecessary HTTP requests we have to send to third-party APIs. Not only can they slow down applications, but they can actually cost us money. So we typically take the user input, we hash it when we look in cache. If we find the corresponding cached content for that ID, the key, we use it. If not, we query the DB, we query the third-party API, and then we cache it in Redis or Valkey with appropriate TTL. And in Valkey, data will look like this: key value pairs with appropriate TTLs. So now let's briefly discuss vector similarity search. So with regular caching and regular search, we're looking for identical matches. But with similarity search, we don't compare strings. We take the text, we convert it into a vector or embedding, and then we compare those for similarity. And vectors are just numbers. They have magnitude and size. So here's an example of vectors in two-dimensional space. You'll see here on the left two vectors pointing in similar direction and of comparable magnitude. In the middle, we have the same vectors, but now they are orthogonal to each other. So that we can see that they are less similar. And on the right, we have them pointing in opposite directions. Well, in reality, we don't have two dimensions. We're going to have hundreds or thousands of dimensions, and vectors will look like this. So we have to go through them and compare two vectors to each other. How do we do that? One approach is something called cosine similarity. And I know we're going to cover a lot of math, or to be more precise, trig and geometry, but it is important. So with cosine of these two vectors on the left, well, they're similar, so the cosine will be close to 1. In the middle, the cosine of 90 degrees is close to 0. And on the right, the cosine of opposite vectors, 180-degree angle, is going to be close to -1. That's a common approach. Another approach is something called Euclidean distance. We use Pythagorean theorem. We basically take x squared plus y squared equals z squared. And if we want to save time and computational resources, we actually don't have to square root it to get the distance. We just need to compare these distances to each other. So the larger the number, the less similar the vectors are. And another common approach is something called inner product. So we take all the components of the vector and we multiply them and sum the results. So here's more math, and we can see that A and B are more similar than A and C. So you want them to point in the same direction, and that'll give you a larger value of the comparison. Another math slide is that we have a concept of unit vectors, or normalized, where we take the length of the vector, the magnitude, and we divide it by, so here, for example, we have a 3 and 4, right? And we compute the magnitude to be 5. And then we divide 3 by 5, we get 0.6, and 4 by 5, 0.8. So the blue vector is the normalized version of the red vector. That is useful for comparison because Actually, for inner product of normalized vector is actually the same as the cosine similarity. You can double check the math, but it'll work. All right. So 3 approaches: cosine similarity, inner product, and L2 distance, comparing angles, directional alignment, and actual distance. But we don't need to compare 2 vectors. We need to compare thousands or millions of vectors when we're doing the vector similarity search. Unless we want to do brute force search, which is a reasonable solution for small data sets, another common approach is something called HNSW, Hierarchical Navigable Small World. And it's essentially a log n time complexity algorithm. What you do is you create multiple layers. And think of a top layer as the highway system. You're going to get where you're going fast, but it has the fewest number of roads and fewest connections. The middle layer is like the major roads in the city. You have more connections. And the bottom layer, where you have all that, it's not middle layer, it's actually middle layers. And the very bottom layer it's like side streets. You're going to get where you're going precisely, but that's what's going to take the most memory, because that's where all the vectors are going to be and all the connections between those nodes. So as you can see, you're storing the same information multiple times, and that leads to a lot of memory usage. So depending on the number of vectors, you're also going to have more layers. So here are some rough estimates. Okay, so how does it all work? Well, you start at the top. You pick a random entry point in the top layer. You then search around it. You find the best possible match. You go to the next layer, and you repeat the process. So here you start with the red. That's your entry. Let's say this is the best match. You drop down. You repeat the process. And you repeat the process. And then green is the best match to your original query. So the benefits are it's going to be much faster, and it's going to be pretty accurate. The biggest downside is memory consumption. Here are some rough estimates. So depending on how many dimensions you have, and that is the biggest variable that's going to drive your memory usage, is that with, let's say, 4,000 dimensions, which is quite common, you will have 4 bytes, float 32 per dimension, 16 kilobytes of data for each vector. So if you have, let's say, 1 million vectors, that's 16 gigabytes of data. And then you have a little bit of memory you're going to use for those graph connections and a little bit of overhead. But this is the biggest number, as you can tell. And if you don't want to use HNSW, you don't have to. Like I said, brute force will work fine. And if you have very large data sets, then there's approaches called inverted file index and product quantization. But HNSW is probably the most common. So let's try to put it all together. Let's say we have a Valkey with vector search module, with Valkey search. And we have 3 documents indexed there. One is called ML definition, and there's a vector. Another is Python basics with its own vector, and deep learning with its own vector. And we're running a query called what is machine learning? Now, we can't compare it directly. We first have to vectorize it. And for that, we have to call LLM. But the difference here is this LLM call is actually very cheap to generate the embedding. What we're trying to do with semantic caching is we're trying to minimize the number of inference requests to LLM, which are very expensive. And I'll show you some financial numbers later. So we take this, what is machine learning, we convert it to a vector by us making that cheap LLM call, and we run it through vector similarity search. And we specify a threshold of 0.90. And we find a match. ML definition is 0.94 similarity to machine learning. That's pretty good. So then we're going to check our cache, because we found the vector, but we want to avoid that call to LLM, and we see, what do we have a cached content? Now, storing a vector without a corresponding cache may be not very useful to you, because the vector is going to take a lot of memory, but vector without caches, what do you do with it, right? You still have to make that LLM call. So you may want to just delete it on its own by specifying a TTL, but we'll talk about that later. But you do have an option of storing vectors separately from your corresponding caches. So anyway, so let's say we found a match for 0.94, we check the cache, and we return ML definition as a response to what is machine learning. Okay, it's similar. But let's assume we don't have this entry in our index. We either can return nothing from our query, and then our application will have to go to LLM, or we can lower the similarity threshold to, let's say, 0.75. And then Deep learning will be the response, and the corresponding cache will be used as the response to our machine learning prompt. Okay, it's kind of similar. Now, if we don't have deep learning, and we lower the threshold even lower to, let's say, 0.5, well, then Python basics will be returned, and the corresponding cache will be used for that. Well, we can kind of tell that Python basics is just not that similar to machine learning. So think of it as like in regular caching, we have a dimension of TTL. So if we cache the data right now for, let's say, weather in Seattle, we'll call some weather API, we'll return the response, and we store it. Well, we know that it's going to be still relevant 5 minutes, 15 minutes, an hour later. But if we cache this data for a week, a month, or even longer, it's not going to be useful. So think of similarity threshold as a separate dimension, right? The more similar data, the higher the similarity threshold is, the more relevant the data is. So if we were to use geography as a proxy for similarity, so weather in Seattle, if you don't have weather in Seattle, maybe you want to substitute weather in Bellevue across the lake. Or if you don't have weather in Bellevue, maybe you go to weather in Tacoma, which is 50 miles that way, I think. If you don't have weather in Tacoma, then maybe weather in Portland, right? And weather in Portland is just not going to be that appropriate substitution for weather in Seattle. So think of these two dimensions. Okay, so let's put it all together. We get the user input, we vectorize it, we check the vector DB. If we find a match, we use the corresponding cached content. And if we don't find a match, then we query LLM. We store both the vector and the cache in Valkey. So Valkey is playing two roles here. It's our vector database, and it is our cache. And it makes it simpler to integrate with it, but it comes with the downside of having to store everything in RAM, which can be costly. When it comes to storing data Valkey, we can model it in different ways. Here are a couple of options. One is we actually store the vector separately from the cache in two different keys. And we use key prefixes to separate them. So key one is kind of like the link between the two of them, but doc and cache prefixes are what differentiates them. Now you can specify the indexes in Valkey search to be only on the keys with prefix doc. So it'll actually avoid indexing keys with prefix cache. And then you'll have different keys for other vector and other cache. And you can specify TTLs individually on cache, but leave vectors around behind. Not sure you want to do that, to be honest. Because, as I said, vector without a corresponding cache, what are you going to do with it? Because what you're really trying to do is save on that LLM call, or save as many of those calls as possible. Another option is you store everything in one hash map. So here you have key one is the key, and then you have a vector, and then a cache value. Again, if you really want to keep the vector around, in Valkey 9, you can specify a hash field expiration, so you set a TTL only on this key value pair, so it'll leave vector behind. Alternatively, you can store expiration time as a field, and then in your client logic, you will check it and decide whether the cache is still valid. And you can store additional attributes such as, for example, user input. Your application actually won't need it because it doesn't care what the input was. It cares only what the vector is and the corresponding cache. But it can be useful for debugging. And if you're debugging, just add it as an attribute and later delete it for production. Because in production, that will cost more memory. So again, why are we doing it? LLMs are expensive. Like right now at work, we are highly encouraged to use AI for pretty much everything. But I fully expect that in a few months, somebody will come along and say, how much is this costing? Okay, so summarize it. If we do it right, we can save a lot of LLM calls and essentially use commodity hardware. If we do it wrong, we're going to have crappy accuracy, unhappy users, and we're going to actually waste a lot of money on RAM. Here are some numbers on what it costs. Embeddings are cheap, inference is expensive. And you don't want to use it when your data is changing rapidly and when you are extremely unlikely to get a second query. So this is very broad guidance. All right, so Valkey search. So what you have to do is you have to use either JSON or hash map data structures. And you have to have a vendor that supports it. So for example, at OCI, we support Valkey 8 with Valkey search. Other cloud vendors also support it. Or if you want to just run your own infra, start up Valkey and just upload the Valkey search module in there. You will create indexes, and then you'll be able to perform searches against them. All right, on to demo. Oops. So here I have a dashboard. where I'm going to specify a query of capital of friends. And I'll specify very loose criteria. And it's going to query a local LLM I'm running using a llama model. And behind the scenes, you will see that there's actually already a query for capital of friends, but there's also a prompt for capital of Germany. So hold on to that. So now I say, let's say, instead of capital of France, I say France capital. OK, Paris, nice. What if I say German capital and I keep my threshold very relaxed? Oops. Oh, darn it. That did not work. Unpredictability limbs. It was supposed to return that Paris, which it usually does, but it didn't this time. So, but bottom line, please trust me. This similarity threshold, again, that is the danger of live demos. You got to like be A, really prepared, and B, you still have an unpredictability. But I assure you, play around with concept of similarity threshold. It was most likely would have returned France as a capital of Germany. OK, let me quickly show you behind the scenes. So again, I have this dashboard where, again, I'm storing these keys separately. And I have the cache key and doc keys, and these have expirations and these don't. So that I use this kind of a hybrid approach to what I was showing earlier in the presentation. A quick jump into the code. So it's built a very simple framework called Micronaut. I have a semantic cache controller. I hit that request. I pass in the prompt. I will basically convert it into embedding. I will store it in Valkey. I will query Valkey index using the hierarchical navigable small world index type. So that is actually created using this piece of code right here, which runs on startup. And it'll create the index. So basically, you see here, and it's an index on type embedding, a float type 32 with appropriate prefix of cosine similarity type. And later, when it runs, it again goes through the whole process that I outlined earlier, where it'll query the index. If there's match found, it'll check the cache. If cache is found, it'll use it. If not, it'll hit the LLM, store the data in an LLM with an expiration. So if you're interested, I'll be happy to share this code with you. It's on GitHub. All right. Are there any questions?